Well, Casey, you know on this podcast, we love stories about heroic nerds.
We absolutely do.
So a couple weeks ago, we had the story of the engineer at Microsoft who may have saved us from a huge, devastating cyber attack. This week, we have a story that I think warms my heart even more.
Yeah, because it's about something that you almost never hear about, which is a aging piece of technology continuing to work.
Exactly, and doing so in space. So this week, researchers at NASA had a big celebratory moment when they learned that they had successfully fixed an old glitchy computer system on Voyager 1, one of the longest operating spacecrafts in history. This is a spacecraft that is 47 years old, which is about your age, right?
It is much older than I am, Kevin. It went into space in a completely different decade from the one that I was born in, but it has been doing amazing work ever since 1977 when it was shot up there.
Yeah, so you could think of this as the most audacious tech support attempt in history because these engineers at NASA were faced with a severe problem. There was a glitch on board Voyager 1. They were getting back this data that they had expected, but it was different. It was just a bunch of ones and zeros.
It was gibberish, Kevin.
It was gibberish.
Yeah, but there was a small, dedicated team that got together to figure out how do you fix a 47-year-old computer
Yeah.
from 15 billion miles away.
Yeah. It is truly a wild story. And I think it's a good chance for us to talk about a piece of the tech world that we don't talk about that much, which is rockets and space. And the fact that, we send all this stuff up into space, all these computers, and then things happen to them. Things go wrong, things break, things glitch. And when that happens, you have two options. You can either let it go and just become sort of a piece of defunct space debris, or you can try to fix it. And this team of engineers at NASA tried to fix it because, as it turns out, this data that it is collecting from Voyager 1 is pretty important. It's giving us information about the outer reaches of our solar system, and it is further from Earth than basically any other piece of man-made equipment.
And not only that, Kevin, but on board of each of these spacecraft, there is a golden record that contain on them greetings from Earth, popular music, and if all goes according to plan, when finally an alien civilization hears these messages, they will decide not to destroy us all.
That's true.
And wouldn't that be amazing?
It'd be funny if the golden record was just a bunch of B-sides from Cher. What was it?
Wait, that would be amazing. What are you talking about?
No, that'd be great.
Yeah.
But I don't think that would further our cause with the aliens.
I'm just hoping there was a lot of Fleetwood Mac on there.
I bet there
Because
was.
if there's one thing that we can all agree on in this divided nation, it's Fleetwood Mac.
And in this divided galaxy. I
Absolutely.
think aliens would like it too. So to talk about what's happening with Voyager 1, this massive tech support project, and how NASA went about tackling this glitch, we invited on Todd Barber. He's an engineer at NASA's Jet Propulsion Lab in California, and he was actually there in the room on Saturday when the team found out that they had successfully fixed this space computer.
So let's make some space for Todd Barber.
Todd Barber, welcome to Hard Fork.
Thank you. I'm delighted to be here today.
So you and your team have been dealing with, I believe, the most hardcore tech support issue that I've ever heard about. So take us back to the time you all started sort of figuring out that there was a technical problem that needed to be fixed here. What did that look like?
Yeah, so taking me back to a very dark day there, but that's okay. That's why we do these things. So it's mid-November of 2023. We tracked Voyager 1 about 1/3 of the time, so basically every day. So we leave our last track, everything's fine, no problems, the data looks great, and then we come up on our next track, and it's just complete gibberish. Voyager 1 is just sending a repeated patterns of 1 and zeros. So no science data, but also no engineering or health data about the state of the spacecraft. So that was a dark day on the project.
Now, let me ask you a very basic practical question. This thing is 15 billion miles away from Earth. How do you communicate with it?
Well, we very slowly, even though the signal moves at the zippy speed of light, 186,000 miles every second, because of that 15 billion mile distance, if you divide those two out, it's about a 22 and a half hour one-way light time. So if there's a problem, it's almost a day for us to learn about it on Earth, and then another day to send up a fix, and that'd be for an instantaneous fix. So it's a lagged conversation, but as long as we're communicating, that's okay. And of course, that was the problem back in November, is Voyager 1 was like a petulant little child, was not communicating.
But like, what kind of signals are these? Like, presumably you're not using, the AT&T 4G network.
No, these are generally S-band signals. It's in the microwave radio frequency spectrum, and don't have a whole lot of competition from other spacecraft in that wavelength band. And it's great. It goes a long distance, and it's kind of tolerant to weather issues on Earth to some extent, because a real bad, we can get rained out like a baseball game if we have a really bad day. But otherwise, that lifeline is this radio signal back and forth. So there's a carrier signal, and then the subcarrier we decommutate on the ground, just like your TV does with the old rabbit ears. You get a signal decommutated. And
I mean, my TV, when I had rabbit ears, couldn't get a signal from about 300 yards away. So these must be a heck of a radio signal they're using up there, Kevin.
Well, I guess on brand for Voyager, I'm still rocking rabbit ears at home too, and it works great. Nice high-def signal.
So Todd, the data that comes off this spacecraft, Voyager 1, what is the data? What are we using this for? Why do we need this data to make its way back to Earth?
Sure. Well, there's the combo. Now, I'm an engineer on the project. I'm the propulsion guy, rocket scientist, if you will. And so I'm looking at the health and safety of the propulsion system, how much propellant's left. I'm like a space plumber. But the real reason, of course, we do the mission is for science. And we're in an area of space no spacecraft has been before. Apologies to kind of the Star Trek reference there, to boldly go. But that's the excitement. We've crossed what's called the heliopause. The sun blows a bubble around itself, and we crossed that boundary on Voyager 1 in 2012 and on Voyager 2 in 2018. So we're the only two working spacecraft outside that bubble in interstellar space. So the key there is, since we're in a brand new environment, all we had before was what are the models tell us this space between the stars is like. And it turns out most of them were wrong, and the scientists love being wrong because then they can go back and refine their models and try to figure out, well, what's really going on out there. So to actually have in situ measurements from not one, but two spacecraft in, outside that bubble, that's the excitement and thrill of Voyager science. And it's hard science to explain to the general public. The cameras are off. It's a lack of pretty pictures, but the science absolutely fundamental.
So back in November, your team starts seeing this incomprehensible data coming back from Voyager 1. It's a very dark day, you said. This is not a fun thing to learn. Now, I want to ask you the question that I get asked every time I call tech support, which is, did you try turning it off and then back on again?
Absolutely, that's a great question. Absolutely, that's the first thing we tried, and it unfortunately didn't work.
So, if it wasn't just about turning it off and back on again, tell us how you actually identified the source of the problem and what it was.
So, through this whole 5-month process, we could tell Voyager was alive, Voyager 1 was alive, and pointed at the Earth, because we were still getting this carrier signal. But that's really just like a flat tone that I'm there. There was nothing that we could decommutate off the carrier signal to get any telemetry. But we did see, as we started trying to change some of the telemetry modes, that some things did change in the subtleties of the carrier signal. So that told us we were commandable. We could get commands to the spacecraft that was interpreting them. So one of the next things we tried was there was a very old program called MinCMROT. And all this would do, it's a very simple little piece of code that would just send 2 pieces of telemetry. But we couldn't test that. There's no test bed. It hadn't been used in decades. But we found a way to upload that, and that worked. So that was a start to diagnosing this problem.
So, okay, let me just summarize back to you what I've heard so far. So you're trying to communicate with the Voyager. You're sending it signals. You're trying to sort of like modify the data that you're receiving from it to sort of test if it's working. Do I have that right so far?
Yeah, and this is just to get a tiny piece of code running to give us just a bare minimum, like 2 checks of a couple of telemetry channels. That's about it.
Okay,
now,
so what happens next?
Yes, so we actually had to go in, and that's scary because it's write protected hardware. So we have to take off the write protection and poke a value in there. And that's really kind of frightening. You don't want to make a mistake there. You could easily kill the spacecraft. So I remember all of us kind of looking over these hex words going line by line till our eyes were, kind of crying, but just making sure every little bit was right so we wouldn't make the problem worse. So somehow all of this, we get a memory readout. And that's when we got this first clue. It looked like one chip, which is about 256 bits, had all of its bits flipped. So that's like a chip failure. So it's amazing, even with no telemetry and from 15 billion miles away and nearly 1 day old data, we said, aha, we think it's this chip. When we started looking at the kind of software things that were on that chip.
And is the
yes.
problem with the chip, as best you understand it, is it age related? I mean, this is a very old computer. It's 47 years old.
Yeah,
that's
correct.
correct.
Put that into context. That's older than Kevin is.
Yeah, that's right.
That's true. So, things start failing in your 30s, I am learning. And by the time you're 47, some of your bits might have flipped. So is that what happened to this chip?
That's one theory and definitely a possibility. The other is that maybe in the, interstellar space is a little more unforgiving in its radiation environment. So we might have had some kind of radiation damage to that chip in this environment. So
I just find it amazing that anything computer related can last for 47 years.
No.
I'm on my 4th pair of AirPods. I mean, I cannot keep a piece of technology alive for 6 months, and you all did it for 47 years. So congratulations
Thank
on
you.
just keeping it alive to that point.
Extremely well built. And I'll say I have a Commodore 64. 42 years old, it still works. I put in the 5.25-inch floppy and play a video game. Oh, the graphics on it are so beautiful. But this is from 82, so maybe they just really built things really well back in the 70s.
That's a true case of they don't build them like they used to.
Absolutely.
So, okay, you've got this chip. It's one chip. It's 256 bits. Its bits have been flipped. It doesn't work anymore. How do you fix that? What is the solution that you all come up with?
Okay, so and a intermediate step before we even did that, we said we want a real calculated MRO. So that's
what is an MRO?
Sorry,
Todd, you have to remember we're idiots.
I know. Oh, bad boy. I use TLAs all the time. Sorry, 3-letter acronyms. I can't do that.
Wait, there's a 3-letter acronym for 3-letter acronyms?
No, that's mine, I think. But
wow.
But anyway, thank you. MRO is a memory readout. So we ended up getting one of those.
Over here. We're huge dumbasses, Todd. Just keep that in mind.
I'll say it. My bits are flipped right now.
Yeah. Okay.
Now that's a useful acronym. Thank you.
Yeah.
So then the idea is that everything that went through that chip, all the code, and again, lack of documentation and no test bed, they had to relocate all of that to free parts of memory. And when you have 69K worth of memory, there's not a lot of free stuff there. In fact, that one chip was 3% of our memory. So we couldn't relocate the whole thing in any one spot. We actually had to break it up into a few pieces. That's scary. And then any dependency of the flight software code that went through that chip, that called other modes and things to other parts of memory, we had to trace all those paths to make sure that none of them would call back to that bad chip. So that took months and a lot of hard work by the team.
And just to sort of reinforce how insane all this is not, when you're talking about relocating things, this is all happening billions of miles away, all through these radio signals that take almost a day to arrive.
That is correct. So we were commanding on about a weekly cadence, and we knew the moment of truth was then about the 18th of April, which was a Thursday. That happened to be our uplink pass that week. So we sent this set of commands, all these hardware pokes, many of them, to specific addresses to relocate all that code. And because of that 2-day round trip light time, basically, we all met about 6 a.m. on Saturday morning, April 20th. And we were in the room, including key members of the Tiger team, not just the Voyager flight team, to see if it would work. We brought our displays up and waited for the magic hour to come.
And how nervous were you? That's got to be a very nerve-wracking moment where you're waiting to hear whether this audacious repair has actually succeeded.
I'm waiting anxiously. I want to see my propulsion data because I haven't seen my ancient spacecraft in 5 months. What other problems, how has it aged in those 5 months? So I'm just really hoping they did everything right from the point of view of getting back to work and seeing the health and safety of the propulsion system.
So take us inside the room at the moment of truth. What does it look like? What's going on?
Yeah, and I
And then
think
what
there's
happens?
some photos that made it out. You might have seen in the media, and it's just all smiles, some high fives. So we didn't miss them like usual. I think there's been some high five training here amongst the engineers and scientists, and a few tears and just massive relief and celebration. I personally had my computer up and just started seeing my first propulsion bits of telemetry come in. The first view into the health of the propulsion system in 5 months. So that was magic. And of course, it was just right to work then for the engineers, because what are we seeing? Is that right? How have things changed, in the last 5 months? But still a moment to celebrate for sure. This was, for the engineers, this was a golden moment, but of course, science is still patiently waiting. We're not an engineering mission. We are absolutely a science mission. So the next step is to figure out, there's 3 other of these telemetry modes that the geniuses in the Tiger team have to figure out how to relocate that code that goes through the failed chip. The good news is the 3 combined is less total code than we had to do just to get the engineering data. The bad news is, we might have to do more of that splicing, a little piece here and there, and check all the dependencies. So we're planning that work now, and hopefully within, let's say, a month or 2, we're fully, and now I'd say we have more confidence that that's going to work because of our success in getting the engineering data back. So once we get this, then we can get all the science instruments back speaking to us and pick up where we left off, with that 5-month gap in the data. But every day, as our project manager says, Voyager 2 sets a new longevity record for a spacecraft since it launched before Voyager 1, and Voyager 1 sets a new distance record for a spacecraft. So it'll be great to pick that up.
When they launched those, how long did they think that they would still be out there doing science?
Yeah, it's a great question. So we launched in 1977, taking advantage of this incredibly rare cosmic alignment of the 4 gas giant outer planets, Jupiter, Saturn, Uranus, and Neptune, that only comes every 176 years. So we were very lucky to have the technology. NASA wasn't even 20 years old yet when we sent Voyager 1 and 2 on their way. And at the time, no spacecraft had really lasted more than a year and 2 in space. So it was already a stretch goal to get Voyager 1 and 2 to a 5-year mark, which is what it would need to get out to Jupiter and Saturn and play all the data back. So not only did we do that, we preserved the option for Voyager 2 to go on to Uranus and Neptune. And by then, we're 12 years into the mission, a huge stretch goal just to get there. That all worked fine. And then since both spacecraft were still working, had some propellant, we realized that they might just, if we were really, really lucky, they might just cross the heliopause. And at the time, the heliopause, this is this edge of the bubble. And at the time, we thought that bubble was a lot smaller than it turned out to be. So as we're going out, where's the bubble? When are we going to cross? And the project nearly got canceled a time or 2. But finally, we had some hints that we're getting close to the edge of the bubble in around 2004. And sure enough, we crossed it in 2012, Voyager 1, 2018, Voyager 2. But I don't think anybody at the time, no matter how well it was built and using the best parts and just really making a mission for the ages, I don't think anyone could have dreamt we'd be here in 2024 talking about with 2 relatively healthy spacecraft.
Yeah. And how much life do you think they might still have in them?
Yeah, that's the big $64,000 question. So we don't know what will end either mission. There's some hard constraints that we know are out there. There's the power source is a RTG, radioisotope thermoelectric generator. We lose about 4 watts a year, and we've already had to turn off some science instruments over the last 20 years. Cameras, for example, there's nothing to see, so might as well turn those off, turn their heaters off. We ended up running out of basically things to turn off, except for the last heaters on the working science instruments. And so we said, well, got nothing to lose. Before you turn a science instrument off, let's turn heaters off. And so we started doing that. And so far, we're 5 for 5. We've put the instruments in an absolute deep freeze to temperatures they never saw during ground testing or in flight, and have no right to still be working, and yet all the instruments are still working. They're pretty cold. We had to recalibrate some things, but they're still working fine. And then we were finally out of power, and we realized we're going to have to start turning off science instruments one by one. Well, then someone said, well, maybe we can let the power margin go negative and go to what's called an unregulated DC bus voltage. And that was not thought possible or was to be avoided. Well, guess what? We tried that on Voyager 2. It worked. So now that bought us another 2 or 3 years. Now, it's a 47-year-old spacecraft. Something else could easily break tomorrow. Every day is a gift.
Todd, is there any fanfare planned for the day inevitably when Voyager 1 is officially retired? Are you going to throw it a retirement party? Does it get a gold watch? What's the plan?
Well, I'm glad you brought up gold watch. That's a very apt description, because our goal right now with both spacecraft, or at least one of them, is to somehow make the 50th anniversary since launch. So a gold watch for the golden record on our golden anniversary. That would be unbelievable. That is August and September of 2027. So maybe 6 months ago, I would say that's looking pretty dicey, but there's renewed vigor now that we've seen Voyager 1, that it seemed to age fairly well over the last 5 months. And Voyager 2 is generally in better shape in most areas. So I think there's definitely a chance to get that 50th anniversary, and that will be a heck of a party.
You mentioned that there is a gold record on one or both of the spacecraft. Is that right?
That's correct. It's identical record on Voyager 1 and Voyager 2. And this is greetings, language, pictures, music from planet Earth. Greatest hits as of 1977. And most beautiful eclectic set of music that you'll hear from planet Earth, just from all over. It's really a beautiful cosmic bottle in the ocean, if you will.
Love that. I love this story. It is such a feel-good story about these engineers who set out to build a thing, and they did it right. They did something right, and it's lasted all these years, and it's giving us still valuable data long after anyone involved with the original project thought it would. I just think it's a very cool story.
Yeah, and we've had lots of miraculous recovery efforts over the years, but I have to say, to me, this one might just be the top of the heap.
Well, Todd, thanks so much for your time. Really appreciate it.
Thank you, Todd.
And congratulations.
Thank you very much. Go Voyager.
Hey, that's the end of this clip. If you liked what you saw, head on over to our page and subscribe, and you can get the full podcast. We do a show like this almost every week on tech and the future. Head on over there now and subscribe.